Hello, everyone. I'm Dion Cook from AVIXA, and welcome to the Transition to Video over IP presented by Richard Ridge. This webinar is brought to you by today's sponsor, Kramer. Before I hand the presentation over to Richard, I need to go over a couple of very quick housekeeping items. For everyone viewing the webinar live today, it qualifies for one renewal unit for the CTS, CTSD, and CTSI. Please allow up to 7 business days to view those on your transcripts. If you have any issues, please email my team directly at webinars@avixa.org. The webinar should last approximately 60 minutes in length, and all attendees have been placed on mute. If you have any questions during the presentation, please enter them into the Q&A window so today's moderator can address them at the end of the webinar. To access the Q&A window, move your cursor towards the bottom of the screen where you'll see the Q&A icon and type your message there. But be careful not to put your important questions in the chat box a couple of icons over from that. You will have access to this recorded webinar at avixa.org/webinars within 7 business days. Richard, please take it away.
Thanks, Dion. Welcome, everyone, to our webinar on the transition to video over IP. As Dion mentioned, my name is Richard Ridge. I'm a Kramer Academy instructor, and I'm responsible for Kramer Canada's national training program. We've already talked about how you guys can ask questions, talked about the AVIXA RUs, so we can start with our learning objectives. So hopefully during this course, we all get to learn something. That's the purpose of being here. We really have 4 learning objectives for this particular course. So number 1, we want to identify the main video over IP codecs and their applications. We want to evaluate the trade-offs between quality, bandwidth, and latency for each of those. And there is, as we'll learn, there's always a trade-off between the codec you choose between those 3 things. We want to understand basic network switch and encoder decoder configuration. I do stress basic. This isn't a network engineering course, but we do want people to know if they're going from traditional Pro AV to video over IP, what's involved in understanding these basic network configurations. And the last one we're going to talk about is bandwidth and how that affects system design. For all the courses I've done over the last probably 15 to 20 years, I never stop talking about bandwidth. We just never have enough of it, and we always have to be aware of it. So here's our agenda for today. It does look like a busy agenda, but we'll get through it. I've broken it down into 6 different sections. So we're going to start with what I think is probably the most important one to understand, which is deployment factors. And I've broken this down into 4 different sections on how complex these deployments can be. It's the biggest question we get if I'm moving from traditional Pro AV to video over IP. What's really involved in designing and deploying a system like that? So I've highlighted in red number 1 because it's by far the most important one. And it's the most important question that you need to ask of your customer is, will the system be deployed on the customer's existing network, or is it going to be a parallel standalone network? That really has a huge impact on how complex these systems are going to be. And it's a decision you have to make with your customer. Number 2, are all these encoders and decoders going to be on a single switch or spread over multiple switches? Number 3, is there going to be other IP-based technologies on the same network? So is this going to be just encoders and decoders with video over IP, or do we have control systems? Do we have things like Dante and QSys on there as well that we have to co-manage and play nice with on the network? Those are all considerations we have to take into account. And the last one is this going to be on a 1 gig or a 10 gig network? I'm sure you've heard all the fights out there about which one of those is most appropriate, but it really is determined by the application. So to make this a little more understandable as far as complexity is concerned, I broke it down into a best case scenario and a not so best case scenario. So my best case scenario, this would be your least complex. This really has nothing to do with the video quality itself. It really has to do with how complex it would be to set up the system. So I've got a highlighted smiley face on this one. So our ideal would be that this would be a parallel standalone network. We don't have to worry about being on someone else's network and worrying about quality of service for IP-based phone systems, for file servers, for email, for surfing the web. We're completely standalone on our system. Single switch would make this a much simpler system, as I'll show later on with some examples. No other IP-based AV technologies. So we've got all the setup that we can do is specific to our encoders and decoders. And the last one is a 1 gig network. It's one of the things you don't hear a lot of people talk about, but in general, 1 gig network switches are typically much easier to set up than 10 gig switches. Biggest reason is because most of them use the standard embedded web page technology that we're used to in Pro AV, whereas 10 gig network switches don't. So the second one I labeled as not so best case scenario with a highlighted sad face. It's probably bad grammar, but it does highlight the fact that these make this system a lot more complex. So on the customer's existing network is really a very big thing that we have to be aware of. If we're involved in multiple switches in our routers, we're going to have to make sure that each one of those is configured properly. If there's multiple other IP-based technologies on there, because then we're going to have to make sure that the setup that we do for our encoders and decoders is also appropriate for the other technologies. And the last one is 10 gig network, because most of the routers by nature that support 10 gig are more complex. And most of them use what's known as command line interface. So they almost use DOS type commands. So, anything that's embedded web pages is graphical. It's very easy to understand and click boxes. Command line interface, you have to understand what the commands are to be able to send them. So that gives you an idea of where the complexity of systems could come from in those two categories. The second part of that section I had there was resolution. So understanding what resolution you need for your application will drive you into a certain codec. So, is this application standard 480p, 720p, 1080p, or is it 4K? And if it's 4K, is it 4K 30, 4K 60? All of those have an impact on the codec that you're going to look at. And typically as resolution goes up, the complexity of the codec goes up, and so does the cost. So we want to make sure we've got the right one. So when I do this presentation as a live presentation, which I used to do before COVID hit, we would go through this resolution calculator, which gives us a very good idea of what resolution makes sense for the application, and then allows us to choose the proper codec. So the variables involved, if I can get my little annotator up here working. So over here, I've got a little section that shows the variables involved if I'm trying to figure out what resolution makes sense. So the biggest one is probably your screen size. And in general, the larger your screen size, the more likely it is you're going to need a higher resolution, like 4K versus 1080p. The second big one is distance from display. So the closer in general that you're going to sit to your display, the more you're able to resolve that resolution, and a higher resolution makes sense. The next two that come into play are application. And if you look at the AVIXA calculators, they're discus calculators. They break it down into analytical decisions versus basic decisions. So if I'm trying to look at engineering drawings, that's much different than if I'm looking at a PowerPoint presentation like you are now. And the last one that comes into play is visual acuity. So how well do people see? Because there is a big variance in how well people see. And in general, the better you see, the further away you can be from a display and still resolve detail. And you'll see in the calculator, we talk about size, we talk about distance from display, and we talk about visual acuity. And then the application determines what else changes from there. So again, this is really trying to make sure that we're choosing the proper resolution for the application. So next section I want to look at is the video over IP codecs themselves. So interesting slide here. The first thing you'll notice is that there's a ton of video over IP or video codecs in general on here. I counted them, there's about 50. So this is a screenshot from Wikipedia. So there's a couple of things that really jump out on this slide here. So the first thing is, you'll notice that the first two standards organizations on here, which are ISO and ITU, they are the two biggest standards organizations in the world. And they've been involved in video codec technology ever since video codec technology was around. And they've standardized some of the most popular ones out there. You'll see number 3 is our friends in the broadcast side at SMPTE. They've been involved in this for a long time as well. So we've got some really heavyweight organizations involved in trying to make these codecs for our applications. So ProAV is not inventing these. These are ones that we're purposing for our applications. The other interesting thing I noticed is way down in the other section, you've got some of the largest organizations in the world, public organizations, guys like Apple, Microsoft, and Google. So when's the last time you saw those three names that were relegated down to the other section? So you can tell that everybody wants to have their offering in video codecs. So knowing all this, how do we choose the right one for our application? Well, luckily, we've narrowed this down a fair bit in the Pro AV space. So one thing we're going to talk about a lot is a trade-off between quality, bandwidth, and latency. And that's really determined by your application. So I've broken this down into two different categories, ones that are designed to sit on a 1 gig network and ones that are designed to sit on a 10 gig network. And really, if you're looking for a product offering to be able to carry for video over IP codecs, you really do need something from the three families we're going to talk about. So I always say something from the MPEG family, something from the JPEG family, and something from the Alliance guys. Because applications dictate that you're going to need something from each of those categories to cover off all your applications. There is no such thing as the world's perfect codec for all applications. It just doesn't exist because everybody has to trade off quality, bandwidth, and latency. So within MPEG, H.264, I mean, it's the most popular codec in the world by far. So anything that lives in that family, H.264, H.265, there's a bunch of other ones as well. We need something from that category, and we'll explain why in a minute. We need something from the JPEG 2000 family or a variant of, because that's great for the Pro AV applications. And then finally, we'll need something from the Alliance guys, whether that be SDVOE. You will find in the Pro AV space, SDVOE as an Alliance is the most popular one. TICO on the broadcast side is very popular, but really we see a lot of SDVOE in the Pro AV space. So I'll take a minute and go through each of those so we better understand, why I've chosen these and why it makes sense. So we'll start with H.264. One thing to not get confused about. So H.264 is the wording that ITU uses, or the naming convention that ITU uses for that codec. Because it is such an important codec, they actually teamed up with MPEG, and MPEG calls it an MPEG-4 Part 10 ABC, a lot longer name. It's exactly the same codec. So they just have different naming conventions, but if you see H.264 or MPEG-4 Part 10 ABC, they're referring to exactly the same codec, just two different naming conventions. It's important to know that it's a lossy compression standard. We'll talk a bit more about that in a few slides, but lossy really means that we're going to throw some stuff away in the encoder that we're never getting back. And sometimes that's just necessary. We'll explain why. There is the big brother to H.264 is H.265, which is really designed to have the same quality with 50% better data compression. And these organizations are constantly trying to improve the data compression so we can get the same quality with lower amounts of bandwidth that we're using. The nice thing about H.264, it provides a high degree of interoperability. Interoperability means I can use a codec from this manufacturer over here, so an encoder on this side, a decoder from a different manufacturer, and they will play nice together. They will actually be able to work together. The big application for H.264 is the wide area network. So if I'm trying to stream information across the public internet, as everybody knows, has limited bandwidth. So we need a codec like H.264 to be able to get that information across reliably. We're not going to be able to stream, a 10 gig signal from SDVOE across the public internet. Just won't get there. It's a great codec for compatibility. So virtually all of your TV, smartphones, PCs, they have an H.264 soft codec decoder built into them. So when you're picking up a stream, it's able to decode it and show it to you. And they're big for recording applications as well. So in our markets, where do we see H.264? On the corporate side, video conferencing is a huge one. So the video conferencing world has kind of, started off with H.263. They've all migrated today over to H.264. And even some of them are moving to H.265 already. But again, because they're using the public internet to move their signals around, they have to have that high level of compression. The other place you're going to see a lot of it is any over-the-top service. So we know those as Netflix and YouTube. Whenever you're watching, if you're watching Netflix these days, for instance, if you're watching a 4K HDR stream from Netflix, that's coming in with an H.265 codec. And if you're watching YouTube and you're uploading anything to it, their standard for uploading to YouTube is H.264. Second one is JPEG 2000. This one is particularly useful for us in Pro AV. It's unique in the sense that you can choose a level of compression, so it can end up being either mathematically lossless, visually lossless, or lossy, depending on your application, all within the same codec. So it gives you a lot of flexibility there. Most of the applications you're going to see, especially in the Pro AV space, uses visually lossless, which we'll explain in a couple of slides. Unfortunately, we have to assume no interoperability. There's some things that JPEG 2000 does with multiple different header types, which means that you really can't use this manufacturer's encoder with that manufacturer's decoder reliably. And if we can't do it reliably, then obviously we don't want to do it. They are working on it, but right now that's our issue. The reason it's become so popular in the Pro AV space is that first bullet point. It really has that really good trade-off between image quality, latency, and bandwidth. Probably the best one that fits our market really well. We have to give up something, but it has a great mix between those three. Application-wise, the biggest one we see is replacing the matrix switcher, especially the big fixed matrix switchers. We have so much more flexibility with video over IP, especially when it's an asymmetrical application. Think of the sports bar application where I've got 8 satellite receivers and 60 displays. I typically have to use a 64 square fixed matrix switcher to accomplish that. In video over IP, we can exactly have 8 inputs and 60 outputs and expand either side as much as we want. It's very flexible. And you will find that a lot of the JPEG 2000 codecs do include video wall functionality as well, which is a nice add-on. So markets, we've seen lots of these go into the corporate higher ed markets. I talked about the sports bars. JPEG 2000 is also digital cinema. So it's the standard. They standardized this years ago for digital cinema. So if you go to any cinema that's running digital projectors, it's based on the JPEG 2000 codec. Last one in that group is SDVOE. So it was designed actually by a company up here in Canada called AptoVision before they got bought out by Semtech. And their implementation is really either uncompressed or mathematically lossless. So anything that's 4K 30 resolution or below would be uncompressed, like completely uncompressed, the same way that HDMI and HD-base-T and DisplayPort are all uncompressed. So would SDVOE. If it's a 4K 60 application, then they use a mathematically lossless codec to be able to put that across a 10 gig network. And it also provides a high degree of interoperability, which is great. So the application really for SDVOE is where compression just isn't feasible. And those applications you can see down are things like medical imaging, command and control, military, live venue. There's certain applications where compression just doesn't work. So take medical imaging as an example. If I'm a doctor and the color of the blood makes all the difference in the world for my diagnosis, we can't be doing chroma subsampling to throw away colors because that would result in a misdiagnosis. So there's absolutely no room for compression in that application. And in things like live venue, we just can't tolerate having latency in our system. So think about those kind of applications where we almost need to have an HDMI type non-compressed situation. That's where SDVOE fits. I've already apologized at the top, said sorry to shout, but really the best video over IP codec is the one that fits the application. And that's why no manufacturer should tell you that, hey, I've got this codec and it's the greatest codec ever for any application you're going to come across. It just doesn't work that way. Everybody really should have something in each of those three categories, whether you're doing wide area network, pro AV, or uncompressed, to be able to fit all of your applications properly. So I've got a slide here on compression types, just one slide. So I've actually sat in the past through 2-hour presentations that explain in gruesome detail how compression algorithms work, but it's way more information that we really need to know. So I've condensed this down to one slide just so we understand the differences. And I can really break them down into ones that are intra-frame and ones that are inter-frame. So intra-frame would be something like what JPEG 2000 uses. So the algorithm looks at the very first frame of information and does its best to find places where it can save on bandwidth. Maybe we've got a huge white wall in the background where we already know what all those pixels are all going to be white, so we can save a bit of bandwidth there. Once it's done with slide number 1, it goes to slide number 2. It no longer cares about slide number 1 or slide number 3. When you look at interframe compression, it's different. It does the first thing on the first slide. It looks for ways to provide cost savings with compression. But then it looks at a bunch of other slides. In this case here, I've got 7 slides in a group. So it has this thing called a group of pictures where it says, okay, I've got 7 slides. I'm only going to encode the differences. So if I'm standing here, or if I'm sitting here right now, and in the picture, I've got my right hand up and nothing else is moving, and the next frame, I slightly move it that way, the only thing it encodes is a change. It says, hey, nothing else in the picture moved except for his arm, so we're just going to encode the changes in his arm. And it will do that for a defined number of frames. And you can see how it only has to encode a very small amount of information for each of those subsequent frames. So because of that, huge cost savings, very high compression levels, very low bandwidth. But it does add latency because it has to go through all those 7 frames first before it can do anything. So this is the kind of a summary sheet between quality, bandwidth, and latency, because it is important to understand. So on the quality side, quality is very much related to compression. So over here, you will see in the top category that if we have something that's uncompressed, it should really say uncompressed or mathematically lossless. Mathematically lossless is we're going to throw something away, but we exactly know how to get it back bit for bit. It's almost like a zip file. And that's what SDVOE uses. Visually lossless is rather subjective. They say we're going to throw some stuff away that we're not going to be able to get back, but we're betting that we can throw away stuff that you can't see anyways. So if we did a side by side, you wouldn't be able to tell the difference. That's visually lossless. Lossy is what H.264 uses. It's saying, I'm going to throw a ton of stuff away, but I think your image is still going to be pretty good. And I think most people are going to be pretty happy with it. Now, if you know what you're looking for and you go up close enough to a display that's running H.264, you might be able to see some blocking artifacts, mosquito noise. If you know what compression artifacts look like, you can typically find them, but you have to look hard for them. So it's good enough for almost all applications except for that really picky person. So that's the quality side. On the bandwidth side, this quality costs. So over here, you'll see this is why SDVOE needs a 10 gig network, because it's uncompressed or mathematically lossless. So it needs that 10 gig network to look after the bandwidth. For JPEG 2000, that number is almost always below 1 gig. And because it's below 1 gig, JPEG 2000 fits nicely on a 1 gig network. And there are different rates that you can use depending on your application. If you look at H.264, that number is way lower. So as an example, Netflix, if you're streaming 4K HDR Netflix, that requires on average about 18 megabits worth of bandwidth. It has to be that low just because people don't have a ton of bandwidth available to be able to receive that. If you were streaming that as an SDVOE signal at 10 gig, nobody would receive it and nobody would be watching Netflix. The latency portion shows up over here. So you can see SDVOE is really low. So people argue about what that number is that people can start to see latency. 30 milliseconds gets thrown out a lot as a threshold. So below 30 milliseconds, really nobody can tell there's actually any latency, even though there is. So SDVOE at 100 microseconds is so far down below, that They call that, zero latency or latency free. It's a bad term. They really should say, so low you can't see it, because nothing is zero for latency. It's always some latency. There's always some finite amount of time it takes something to get from here to there. JPEG 2000 typically can sit in the 20 to 40 range in Pro AV environments. So really it's not an issue. H.264 has lots of latency. Now in the application, do we care? So if I'm doing this presentation in this room that I'm in here now, and I'm using H.264 codecs to send this maybe down the hall to another room, as long as my audio and video are in sync, do you care that you've got 500 milliseconds or a second worth of latency? No, because you can't see me live. You're not using a mouse and chasing that around a screen. They're getting that presentation a second after I present it, but it doesn't matter because they can't see me live. So really H.264, don't use that in room, but certainly you could use JPEG 2000 or SDVUE as an in-room application. Okay, we're going to go over some video over IP configurations. So I've got a few of these on here that I'll go through pretty quickly. You'll recognize almost all of these from the Pro AV space, but I want to kind of compare and contrast what these look like. So the simplest video over IP system, believe it or not, could be as simple as one encoder going directly into one decoder. No network switch, just a direct connection between it. It almost looks like an HD-base-T transmitter receiver set, although it's using IP instead of what HD-base-T uses. But this could be your simplest video over IP system. I'm not sure the application for this one here, because I probably would use HD-base-T based on the cost difference between the two, and knowing that HD-base-T is a uncompressed technology, but it does exist. This is an interesting one, one-to-many. So if you took a media player and fed it into an encoder, and then went into your first decoder, and then came out of that decoder into the next decoder, and so on and so forth, you could daisy chain these realistically as long as you wanted to. That IP signal gets rebuilt as long as it's below that 100-meter limit. It gets rebuilt within every unit, and essentially you can do this daisy chain for as long as you want. We really can't do that in HD-base-T. It has an 8-hop limit, but this you could certainly do for pretty much as far as you want. If this was digital signage in a mall application, for instance, this might be a neat application for it. Next one is our good old friend, the DA. So this one here would be the equivalent of a 1-to-3 HDMI DA, for instance. We have an encoder going into a switch and then going out to 3 decoders. The big difference here is we really have no limit with video over IP. So if this application was 1-to-3 and we happen to buy a 1-to-3 HDMI DA and they want to add one more display, we'd either have to sub out that 1-to-3 DA for a 1-to-4 DA, or we'd have to jump out of that 1-to-3 DA into another DA to get that extra one on there. With video over IP, as long as we've got ports available, we could make this as big as we want. 1-to-3, 1-to-30, 1-to-300. There really is no limit as long as we've got the ports available. And there are lots of ways of adding ports to switches, to stack switches, to get really as many ports as you need. Interesting thing that a lot of the codecs offer video wall functionality. So this here could be a 1-to-4 DA application, and by sending a control command, we could turn this into a 2x2 video wall application. And a lot of these ones here will go up to 16x16 video walls. So it's just something that a lot of these JPEG 2000 codecs have built into them that we could take advantage of. This is our real application in Pro AV for video over IP, which is replacing the matrix switcher. We all know the problems we've had where we sell a customer a 16x16 fixed matrix switcher. They've loaded up the back end. They've got 16 displays on there. They want to add that 17th display. So our options are we either have to replace the matrix switcher with a 32x32, or we have to start using DAs and sharing displays, which they're not always fond of. In the video over IP world, we can make these as big as we want. Again, it's just ports. We could make this, a nice thing, we can make them asymmetrical. So again, for restaurants or for sports bars, we could make it 8x64 and just use 8x64 number of ports. We don't have to waste a bunch of input ports that we're not going to use. A unique thing for the SDVOE guys is some of their codecs support not only video walls, but multi-viewer functionality. So we can take multiple images and we can tile them in different forms or fashions on the displays, in addition to doing video walls. So that's a nice add-on to SDVOE codecs. And the last one that we sometimes get involved in our space, but not very often, is KVM. So again, we could take multiple computers, run them into encoders through a switch to a decoder, and now we have access to do KVM switching from a single display for a command and control type application. So that covers off the video over IP configurations. We're going to jump into to network switch configuration. Again, I stress this is going to be the most basic part of network switch configuration. We're not going to make you guys network engineers in the next 20 minutes, but I do want you to have a basic understanding of what's involved in setting up a network switch for video over IP. The first thing I noticed, and maybe you've noticed as well, is when I first opened up the Luxel switch that I have in my demo kit, which is at the back of the room over there, I found there was a whole bunch of acronyms that the network switch guys use that I'm just not familiar with. And it's a little intimidating to figure out, well, which one of these do I need to set up a proper video over IP network? So luckily, it's not as hard as it first looked. So there are some basic network switch requirements that no matter which manufacturer you're working with, they pretty much all have the same requirements. So I'll go through all the ones that come up time and again. So the first thing they'll want is a layer 2 or layer 3 managed switch. And a managed switch is important because that allows you to go in and change settings. And you'll see us doing that in a few minutes here. A non-blocking backplane, tongue twister, because we want to be able to send any of our sources to any of our destinations without restriction. Thing called jumbo frames we'll talk about. We'll talk about IGMP as a protocol. Multicast is very important to make sure we're not flooding our switches. And strangely enough, we're going to disable green features in this green world. We'll explain why. So the first thing you'll want to make sure you have a look at is managed switches allow you to go in and configure your switch to match up to your application. So again, no matter which manufacturer you're working with, you should see a diagram like this or a table like this that shows you how they want their switch set up for video over IP. So most manufacturers will tell you that they are switch agnostic, that they don't really care which switch manufacturer you use, as long as they're able to look after everything on the table here. If you can configure these, then you don't have to use switch A or switch B. As long as the switch allows you to configure these settings, you should be good to go. Luckily, there's a lot of switch manufacturers who see the people from the Pro AV coming their way, and they've made this a little easier by giving us configuration files. So for instance, the switch I have in my demo kit is a Luxel switch. So they've given us a configuration file that all we have to do is take that file, upload it to our switch, and we're 95% of the way there. All the configurations that need to be done are taken care of in the configuration file. One big note, just make sure that if you're on a customer's network, that you don't upload a configuration file on a customer's network. This only works if you're on a parallel standalone network, because you don't want to change their settings. I mean, they wouldn't let you do it anyways, but just make sure you don't do it. So I'll go through a couple of those terms. I threw out the more important ones. So jumbo frames is really about trying to efficiently move around video traffic. So one of the things about video versus regular data, like email, for instance, there's just way more information we have to move around there. So we want to do it efficiently. So the standard for moving around, Ethernet frames is 1,500 bytes. So you can see in the graphic below, if I was trying to move around, 9,000 bytes worth of data, I could either send 6 trucks. And the problem is every time I send a truck, I send one truck, I have to talk to the processor, say, hey, did you get that? Yep, got it. Okay, send the next guy. There's a lot of communication going back on and forth with the processor. If I send one truck that's got a bigger load, I only have to do that once. So we can move around information a lot more efficiently with jumbo frames. And that's really all jumbo frames is. And it could be as simple as in my Luxol switch, I set my maximum frame size to as large as it will let me. In this case here, it let me set it to 9600. And that way I know I've got jumbo frames enabled and I can move that data around more efficiently. The next one is casting technologies. There's 3 of them that are going to pop up. Unicast is a one-to-one connection. All of these have their place, but multicast is the one we're most interested in. So unicast, again, is that one-to-one connection. Broadcast, just like it sounds, you send one thing everywhere. And multicast, it only sends out the stream to the people who request it, which makes it very efficient. So you can see here again on my configuration on my Luxol switch, I am indeed running multicast. Nice little pictorial to drive this home. So again, unicast is sending one source to only one destination. That's how things like Netflix and YouTube work. They have to work that way because you're constantly going in and pausing and fast forwarding and changing things. Broadcast is one to everywhere. Broadcast doesn't care if you're listening or not. So that would be your satellite receiver. Whether my satellite receiver is on or being used or I'm on a different device, it's always sending the information to it. If I happen to use it, great. If I don't, great. Whereas multicast is very dependent on, hey, I want this stream. I'm going to send it to you only, but only the people who request it. So a couple of examples should drive home what this means to bandwidth. So let's say I've got an encoder that requires 400 meg worth of bandwidth maximum. So I got that from my spec sheet. And I've got a 1 gig switch. So what happens? I add a decoder, and that decoder says, hey, I want to get that stream from that encoder up there. Encoder says, fine, here's your stream. That cost me 400 meg through my switch. It's a 1 gig switch, so I'm fine. I add a second decoder. The encoder says, okay, since we're unicast, I'm going to give you your own unique stream going into that same port. So now I've got 800 meg going into a 1 gig port, so still good. So you can kind of see where this bus is going. I add that third decoder. The encoder says, well, here's your stream, but now I'm trying to send 1.2 gig into a 1 gig switch. Now I've put an X down there, but what typically happens is the system will do its best to try and, even though it's oversubscribed, it will do its best to try and feed video. But this is where you start to see drop frames, loss of video, choppy video. You've created a problem. And you can see how this doesn't really work for our applications. In multicast, same scenario. I add a decoder, but the encoder now sends a stream to the switch and it's done. I add a second decoder. The switch is now responsible for duplicating that stream and sending it out. So I'm still only sending a 400 meg stream into the switch. And my switch says, okay, out of a different port, I'm going to send out that other 400. I can add a third one. I can add as many as I want. I'm never going to get myself in trouble if this is a standalone system because I'm using multicast. So that's why we want to use multicast for our video over IP applications. So IGMP is a protocol that works in conjunction with multicast to make sure that we're not flooding the system. And I'll kind of walk through a couple of these quickly to show you how it works. They got some strange terms. So IGMP snooping, you'll hear about, that really allows the switch to listen to the conversation between the encoders and decoders to figure out where people are and who's on the system. Which goes into number 2, which is snooping group information. So the switch actually builds a table so it can keep track of where everybody is. And I'll show you what that table looks like in a minute. The querier is just a function that goes out there and says, hey, still there? Are you still there? Are you still there? It's almost like HDCP in an HDMI system. It always wants to know if that person is still there. And fast leave allows us to do quicker switching between sources. So you see IGMP has 4 different components that all work to make our systems more efficient. And here's how it works in a pictorial. So if I happen to be this subscriber down here, and I want to request a multicast stream from up here, when it hits that router has no idea where I am without IGMP because it's not keeping track of me. So it floods the network. It sends it to all the switches and to all the hosts. With snooping activated, same scenario, this router says, I know exactly where this guy is because I've gone to lookup table and I can see it. So I'm only sending my information to this switch. That switch says I'm only sending my information to that switch. And that switch says I'm only sending my information to the guy who subscribed it. You can see how much more efficient that is it prevents us from flooding the network. It's a very easy thing to enable. It says snooping enabled, and we put a check mark on there. It's that easy. So this is the group information table that the switch maintains. So when we set up multicast, what the switch will do is we'll set up multicast groups. So this is actually a screenshot from my demo system. I have an encoder decoder pair on channel 1, multicast group 1, and an encoder decoder on channel 2. So when we do this live in class, what we do is we actually take the decoder, which is number 6, and I say, hey, instead of listening to encoder number 1, we now want you to listen to encoder number 2. And in real time, you'll see that check mark moves down there. So as soon as we make that change on the decoder, the table makes that change so we can keep track of where we are, so it knows where everybody lives in the system. The querier is just something you have to set up. There's a few different versions of it. You'll see most people will use IGMP version 2, only because version 1 doesn't support fast leave, which we'll talk about in a minute. And version 3 is the latest version, but has a whole bunch of other overhead features that we really don't use in video over IP. And for enabling fast leave, what fast leave does is, as soon as we're changing from listening to encoder number 1 to encoder number 2, it sends a fast leave message to say, hey, I'm leaving 1 and I'm heading to 2. So it immediately drops that connection. So it allows it to drop stream number 1 so it can pick up stream number 2. And again, it's as simple as a checkbox. I check that off for all my ports, and that way I've got fast leave enabled so I can get that faster switching. The last one in this section here is for green power features. It's odd in this day and age to turn off green power features, but if we optimize for power, because all these devices are using PoE, if I put my encoder to sleep and now I want to switch to it, it now has to wake up. It probably has to yawn and have a coffee before it's ready to switch. And we don't want that. We want fast switching in our systems. So if I optimize the system for reduced latency, I can get my quicker switching. That's why we turn off those green features. We'll take a sec to walk through PoE. Everybody, I'm sure, is aware of PoE, but there's a couple things that when you're using video over IP that are good things to know. So their nomenclature for a PSE is a power sourcing equipment. That's really just a network switch, or it could be an injector. It's the guy who's providing the power. And you'll see PD, or power device. That's the guy who's receiving the power. In the IT world, that's access points, IP cameras, VoIP phones. For us, it's encoders and decoders. So believe it or not, they actually have 4 different standards. So what we call PoE is really the type 1 standard, which delivers, in this case here, it says it delivers up to 15.4 watts of power from the source, but we only guarantee 12.95 at the destination or at the decoder because of line loss. PoE Plus provides more power, and you can see we've got PoE Plus and high power PoE. The reason this is important is because in the Pro AV world, we do have codecs that support all 3 of those. So if you have a codec that requires PoE++ in order to power it, you have to buy typically a much more expensive network switch because it has to have a much bigger power supply to be able to supply that 60 watts worth of power to every port versus a standard PoE switch, which are very inexpensive. It does make a big difference on cost. So we need to understand PoE budget. So for a quick example, if you looked at in my demo kit, I looked at my encoders and decoders. So from a spec sheet, there's what my encoder requires. So every one of my encoders requires 6.72 watts maximum worth of power. And my decoders are a little bit more, probably because I have a scaler in them, at just over 8. And if I look up my switch has a 130 watt power budget. So what does that all mean? So if I look at scenario number 1, let's say I had 1 encoder and 7 decoders. I do that math, it comes out to I require 68 watts worth of power to drive all those by PoE. Well, luckily I have 130 watts available from my switch, so no problem at all. Let's say scenario number 2, I have some different encoders and decoders that require full PoE capability, the full 15.4 watts. That comes out to 123. I'm still good, but just below the 130. Scenario number 3, because my switch does support PoE plus for power, if it required the full 30 watts of power, I'm now at 240. I'm well above my 130. So when I do this class live, I ask the question, assuming we can't replace that network switch, what options do I have for powering the remaining encoders and decoders? And those answers are either a local power supply on the extra ones or a PoE injector. On the configuration side, you can see down here for every port, you can decide whether it doesn't need PoE disabled. You can give it standard PoE or PoE plus. One thing that you'll find that a lot of IT people will do is they'll actually run. This is a screenshot of from my switcher live. And if you look at numbers 2 and 6, so number 2 is a decoder and number 6 is a decoder. They're using well below that 8.8 watts required. So sometimes the IT guys will look at this over a period of time to figure out just how much usage that device really needs and develop their power budget that way. So they're not having a whole bunch of wasted power or paying for power that they're never using. Okay, so our quick last second section here on encoder decoder setup. So now we've set up our network switch. We also have to make sure we set up our encoders decoders. They typically have some settings and embedded web pages that we need to look at as well. So on the encoder side, it's important to make sure we set up multicast in our network switch. We also have to do that for our encoder. The other thing you might want to look at, if it's available for your encoder, is the maximum bit rate. So I've got mine set to best effort because I'm on my own switch. There's nothing else on there. So I want that thing to have all the bandwidth it needs. If I was on a customer's network and they had quality of service and they said, hey, Richard, I can only give you 100 meg worth of bandwidth, I'd rather have that 100 meg set up in my encoder than have them throttle me downstream when I'm using too much. So it's better to set it up in the encoder there. On the decoder side, same thing, make sure you set your decoder to multicast as well. In our last section, good old bandwidth. It's a bit different than we were used to when we talk about, and we've talked about this for years, HDMI bandwidth or HD-based bandwidth or DisplayPort bandwidth, it's always fixed. We can always do the math and get an exact number every single time, regardless of what we're playing for content. Whereas video over IP varies continuously depending on that content and depending on some other things as well. The biggest one is probably our starting bandwidth. If we start with, let's say, 480p from YouTube versus starting with 4K 30 from a Blu-ray player, it's a huge difference in the amount of starting bandwidth we have. So obviously it affects how much compression and how much bandwidth we're going to use. Scene complexity makes a big difference. You know, do we have a static slide like I have right now on PowerPoint, or do we have a lot of motion? Is this a video where we have a lot of motion and a lot of color and contrast variances? Compression type we talked about, and we also talked about compression ratio. So all of those things factor into bandwidth. So as an example, if we take our good old 4K 68-bit 444 signal, which we all know and love, in the HDMI world, you know, we've done that math forever. It's 17.82 gig no matter what. For video over IP, a couple of things are different. So first of all, you'll notice that the blanking period that we have to use in our HDMI calculations, we don't need for video over IP. That's an HDMI thing. We also don't need the overhead bits here as well. So we can get rid of all of that. So on that same signal, our starting bandwidth is just shy of 12. The important thing is it's over 10. So we can't fit that as is on a 10 gig network, especially the SDVOE guys. So that's why they need to have that 1.4 to 1 compression with this signal to get it below 10 so we can actually fit that on a 10 gig network. That's why they have that compression. So what we did to kind of show how this bandwidth varies is we had before SolarWinds had their problem. we had the SolarWinds software that did the real-time bandwidth monitoring for these different signal types to show how they vary. So to give you a few examples, this is a still image at 1080p 60. And you can see what we did is we took in this case here, a laptop into an encoder, which came into port number 2, and we measured the bandwidth. And you can see we're using about 3 mega bandwidth with some spikes. We've got a 1 gig switch, so we're using almost nothing. If we then go to a PowerPoint presentation, again, almost nothing except for when we have those fancy slide transitions with lots of motion, you can see we get some spikes in there, upwards of 60 or 100 meg, still well below a gig. When we get to YouTube and a mini player, now you start to see, because we've got moving video, we're around 20 steady state. When I get to YouTube for a full size or regular size browser, we're up about 150 on average. So we're starting to get some bigger numbers. And full screen YouTube, and all of this has been at 1080p 60 up to this point here, we're up around 200 megs. We're starting to see some bigger numbers. Again, if I'm on my own switch with my own bandwidth, don't care. If I'm on a customer's network, care a lot. They want to know how much bandwidth we're going to use. Last two examples, Blu-ray at 1080p 60, I'm at about 250. Blu-ray at 4K 30, I can get well up into the 3s with spikes all the way to 7. So again, this is information that IT guys are going to want to know if you're putting it on their network. So last couple exercises before we wrap up here, understanding bandwidth requirements on single switch and multiple switch scenarios, which we talked about before. So if I have a single switch, so right here I have a 24 port switch, which is a 1 gig switch. I've got 12 encoders. Let's say for argument's sake, they require 400 meg maximum and 12 decoders. I can't get myself in trouble anywhere. I could have 23 encoders and 1 decoder, 1 encoder, 23 decoders, any combination, can't get myself in trouble. So this is why a single switch scenario gets rid of some of that complexity. No switch math involved. As soon as we go to 2 switches, then we need to do some switch math. In this case here, I've got 4 encoders on switch 1. I've got 6 decoders on switch 2. And let's say for argument's sake, I've got a link between the two. I'm using link aggregation group to create a virtual 2 gig link between the two of them. So in this case here, at 400 megapiece times 4, I've got 1.6 gig worth of bandwidth going from switch 1 to switch 2, but I got 2 gig available, so I'm fine. And again, if I had a bunch more decoders, it doesn't change anything because the switch itself is replicating that signal because we're using multicast. Another way of doing this, you'll find a lot of switches have SFP plus ports, which is a bi-directional 10 gig channel between the 2 switches. So in this case here, even with 12 encoders at 400 meg, I've got lots of bandwidth available. I need 4.8, I've got 10. My last picture, I've got, in this case here, similar to what we had before, we know we're fine already. So when I run this live, I say, is it safe to add more decoders on that first switch? It is, because all of our encoders and decoders are on the same switch, and we know that works just fine. So I said, yes. The tricky part comes here. Is it safe to add more encoders on the second switch? So it is for this reason here. So you'll see that we need 1.6 going back the other way. So these switches really need to get that way. And they also go this way. So because it's bi-directional, the bandwidth is bi-directional, we can have those encoders go simultaneously one way and the other way at the same time. So in summary, before we hit questions, it is important to match up the codec to the application. It's probably the biggest thing to make sure you do. Make sure you've got the appropriate codec for the application you're working on. Always be aware of that trade-off between quality, bandwidth, and latency. You just can't get around it. Check to make sure we've got the network switch or switches configured properly so we don't run into issues, and make sure we have enough bandwidth in the system so it's a non-blocking system, so we can really send anything anywhere. And that's it for me. It looks like we've still got about 5 minutes left, so I'll let Dion come back in and see if we have any questions that hopefully I can answer for you.
Okay, Richard, yeah, we do have a few questions here. So the first one is from Jose, and he asked, do you think H.266 will be adopted soon and H.265 will die an early death before having a chance to get used?
it takes a long time for any technology like that to be adopted and be the one. So you look at H.264, it came out 15, 20 years ago, and it's still the most prevalent technology out there. So I know ITU and ISO are always trying to improve the compression algorithms that go into these things. So sure, over time, we'll go away from H.264. H.265 will be the big one. H.266 will be the next one everybody's looking at. But it always does take time for that technology to move, because so many devices already have certain codecs in them that you need those next gen devices to adopt the technology for it to really take off.
Next up, Doug asks, what about incoming codecs such as Silex Insight, Colibri, and IEEE supported AIMS IPMX codecs?
So the AIMS one's interesting. They're trying to standardize codecs, trying to have a standard, because right now, Pro AV is in the Pro AV side. It's always been the Wild West. When we moved over to codecs, everybody wants to have their own proprietary way of doing things. So you can't typically use, in a lot of cases with JPEG 2000 especially, this guy's encoder with that guy's decoder. And really, guys like AIMS are trying to standardize on a system, just like IT is standardized for PoE, for instance, very well standardized. So everybody's devices all work nice together. And that's really what AIMS is trying to do. It'll take them some time because it's not in the manufacturer's interest. When they support things like AIMS, then you can really use anybody's product. And selfishly almost, it doesn't allow them to have to someone just be standardized on someone else's codec.
Okay, from an anonymous attendee, you mentioned H.264 and 265. What, if anything, do we need to know about H.266 at this point?
That's very similar to the first question. The fact that ITU and ISO are constantly working on next generation devices, but you typically don't see them until those devices come out and actually have either those hard or soft codecs supported within them to be able to support the standard. Are we moving that way? Absolutely. It's just a matter of time where some of the legacy H.264 devices get replaced with newer devices that support those codecs, especially H.266.
Johnny asked, what compression category do TV broadcasters use for cable TV distribution?
So they actually use a whole different system. So they use, depending on where they're from, they may use QAM, they may use a couple different ones I can't remember the acronyms on. So they have a different way of doing it. So they do use compression algorithms in the same way that H.264 or JPEG use. They just use a different technology to do that based on the way that they have to transmit.
Okay, next up, Jose asks, would you agree that the device where content is consumed also impacts perceived image quality? An iPhone will accept H.264 images and better than a 50-inch display.
Absolutely. Yeah, so a lot of that has to do, even when we have something like H.264, there are quality differences between how they're implemented. And a good example is JPEG 2000 can be either lossy, visually lossless, or mathematically lossless. So the version of JPEG 2000 as an example that digital cinema uses is far different than the version of JPEG 2000 that we use in Pro AV in our codecs, even though they're both called JPEG 2000. The amount of compression they're using in the application absolutely affects the quality you're going to get in your device.
Amit is asking if you will share the slide deck with the attendees.
Yeah, absolutely. If you guys want to send me an email at rridge@kramerev.com for anybody who's interested, we'd be happy to, I can work with our marketing department to share that with you.
Okay, Nathaniel asks, what does Netflix use? HD?
So Netflix, it depends on the device you're actually streaming to. So I mentioned as an example, if you're sending 4K HDR signals, they're actually using H.265 codec. But if you're sending Netflix to your phone, like my daughter prefers to watch Netflix on a phone, they actually use a different codec. They don't use H.265. They use, it's not coming to me right now. I think they're using the new AO media codec, the AV1, but I'm not entirely sure. But manufacturers will use different codecs depending on the devices that they're sending the information to.
Samuel wants to know, what's your opinion on the use of NDI instead of encoders and decoders?
So I guess the biggest difference is NDI is a proprietary technology from, I believe, NewTek. Whereas if you're talking about something like H.264, it's standardized by a standards body instead of being standardized by a manufacturer. So, the open source support that you can get from things that come out of ISO and ITU means that it's going to be a lot higher adoption rate just because everybody has access to it, more so than when you have something like NDI coming from a manufacturer.
Okay, the last question up is can you please provide your email address again?
Sorry, so it's rridge, so RRIDGE at kramerav.com. And then what I'll do is I'll work with our marketing department to make sure anybody who wants the slide deck has access to it.
Okay, actually, we got one more that just came in last second. So this will be our last one, guys. It is from Gregory. What percentage of projects are you seeing going to a networked AV model?
Tough number. We get asked that a lot, and the number is changing all the time. I will tell you that if it happens to be a matrix application, my guess these days, the larger the matrix, the higher the number. So if it's something where where they used to sell a 64 by 64 matrix, I bet you 80% of those are now video over IP. If it happens to be a smaller 8 by 8 fixed matrix, it's still a lot less expensive to use a fixed matrix if you don't need expandability. But for sure, that number is getting higher every day.
Okay, hey, Richard, thank you so much. And I'd like to thank everyone for attending today's webinar, and thank you for joining us for this webinar today, which is Transition to Video over IP. This recording will be available on our website, avixa.org/webinars, within about 7 business days, and your one renewal unit will be applied to your transcripts within those 7 days. If you have any trouble, please email my team directly at webinars@avixa.org. Just a side note that's important for you CTS holders. If you've registered for this webinar with an email address other than the one I have on file for you, you can't get credit for attending. You'll need to contact my team and have us corrected for you on the back end. Simply email your account rep, whoever that is, and let them know that you use the wrong email address when you registered, and we'll get it fixed for you there. So I just want to thank today's sponsor, Kramer, and a huge thank you to Richard for helping us to understand the transition to video over IP. We hope you've enjoyed this. Please stay safe and make it a great day, everyone.
Yeah, thanks, guys.